So we'll start here. We've got two boats that have just rounded the windward mark, and we're heading downwind. We'll say one of them's on wing, right? And we'll say the other one goes to a reach. So the idea that this boat is working off of is that he's going to be able to go farther out with greater speed and then come back ahead of red. So this boat is moving faster in this direction than this boat is moving in this direction, right? The question we have to ask ourselves, we're moving faster this way, but we also have a longer distance to go because we're going to be going out like this and then back in, right? Whereas this guy is just coming straight down. So just like we were thinking on our upwind, is the extra speed that we get from reaching going to offset the extra distance we have to sail by reaching? So let's look at that. And for this, we can actually pull out a little bit more numbers. This is a little easy because of the way this is kind of bigger angles. It's easier to deal with than kind of small couple degrees differences for the upwinds. So let's take a random angle. I think if we call this maybe 30 degrees, I think that'd be fair, right? So this guy's heading straight downwind. This guy's going to be kind of an angle of maybe 30 degrees off, right? So if we remember from geometry or whatever it is that we learn everything about angles and stuff, right? We got 30 degrees here. What's the, well, that should be inside. What's all our different side lengths here, right? So we have 1, square root of 3, or roughly 1.7, it's like 1.73. That's good enough for our calculations here. And then our hypotenuse, the long leg, is going to be 2. So if we turn that into this triangle here, this is going to be our 1.7, right? And this is going to be our 2. So if we are going, we'll make up a random number, say 5 knots in our boat that's running wing on wing. Going 5 knots downwind, right? That's I'd say that's pretty fair for a wind of maybe 8 to 10 knots. That's probably what you'll get in your FJ if you're going wing on wing. Let's find out what speed our reaching boat would have to be if we were to go and meet perfectly back at the leeward mark without either boat beating each other. So we hop in our calculator real quick and we'll divide 5 by 1.7. Look at that, 2.94. So let's say, we'll just say 3 for simplicity. So if we multiply 2 by 3, that means we have to be going roughly 6 knots on the reach here if we're going to go out and back and come back in at the same time as a boat that's wing on wing. So that means if we don't go at least 6 knots, we're not even going to break even. So maybe the extra speed we get only brings us up to 5.5 knots from when we started at 5, right? That means that this boat that's taking this extra distance is not going fast enough to make the extra distance worthwhile, and so the boat that's running is actually going to beat him back down to the leeward mark. So this would also work in lighter winds, right? Maybe the wind is only about 4 to 5 knots. It's a very, very light air day, and so maybe our speed when we're going downwind is only 2, right? Only 2 knots. So let's find out what that would have to be, what we'd have to do on the reach in order to beat it. So if we do the same thing here, we got 2 divided by 1.7, and that means we only have to come up, let's say that's 1.2, just to be easy. So 2 times 1.2 is what? 2.4. So we only have to come up to 2.4 knots in order to break even on the run. Here's the secret about light air, right? If we're on the wing on wing, right, and we're going 2 knots, that wind is so light, it's going to be a very big speed difference. As soon as you add the pushing and that kind of pulling forward motion, as soon as you add that in, your speed really increases, and you're going to be going a lot faster than just 2.4 knots, right? So that's why in light air, we often say, don't run or don't do wing on wing, go for the reach, because your speed might come up to 3 knots. And that's obviously not super huge. It's the same speed increase, 1 knot, as we saw for the higher wind, but it's a bigger percentage increase, right? And that's kind of what we're looking for here. This boat is going faster than it needs to break even, Thus, he's going to beat the boat that's running down to the line, right? He'll go over and jibe here, and he's still moving faster, so he's going to draw ahead of the boat that's trying to run. That's why we say in lighter air, you're going to want to do the reach instead of the wing, because it's just going to give you, it's going to give you longer distance to go, but greater speed. And that greater speed is usually going to be enough to offset the longer distance. Alright, so let's kind of look at why in heavier winds it becomes typically better to do the wing on wing instead of reaching. Even though, like, if we look here, here's 5 knots, we only have to get up to 6 knots. Why would that be a problem? Why wouldn't it be, why couldn't we get up to a speed even more than that when we're reaching? We saw it works out fine in lighter air. Why doesn't it work when we start getting more breeze? Why does the run usually work out then? So for that, we need to look at this concept, hull speed. And so this is basically saying that for a particular boat shape and size, there's a certain speed at which it can't push any faster through the water. You can add more power, you can add more wind or horsepower in your motor or whatever your boat happens to be run on, but at some point all that's going to happen is you're just displacing more and more water in front of you, but not actually moving the boat faster. If you can start planing, if your hull comes out of the water, then the hull speed equation kind of goes away. That doesn't matter anymore, and that's why you see all those fast motorboats now have planing hulls. That's why in sailboats going downwind in heavier wind, we want to try to get planing, pop the hull out of the water, because that lets us go much faster. So there's actually kind of a handy little equation that we can use here. It's actually much simpler than you might expect. It's 1.34 times the square root of the water line of the boat. I don't know the exact science behind why it is the length of a boat that determines how fast it can go, but that's what a lot of people who've done experiments and stuff with this have worked out. And the answer for this will be some speed in knots, right? So they've worked out a very handy equation for us to use, and the FJ is a little bit short of 14 feet long, but we can use that, use 14 feet as a pretty good estimate. So 1.34 times, I've only got my phone calculator with me, but if we say, maybe that's probably about 3.7, something like that. Let's check 3.7. Yeah, look at that, that's almost perfect. So 1.34 times 3.7 equals just about 5 knots. I'd say that's enough that we could say basically 5. So what's happening here is that at any winds that are not strong enough to make your boat plane or pop the hull out of the water and skate along the top, you're really not going to go much faster than 5 knots. As the wind picks up, you'll feel more power in your sails. It feels like you're getting faster. You see all the huge bow wave going on, but that's really all that's happening, is your boat is just pushing more water out of the way. It's not actually moving faster. So if we go back to this example, at 5 knots, it turns out this is kind of the top speed of our FJ, right? So whether it's 10 knots of wind coming down or 15 knots, we're actually not moving any faster. And that's why suddenly we need to be more than 5. We're not going to get to 6, right? If we're just in displacement mode, pushing water out of the way, this is probably more about 10 to 15 when this will happen. So we're looking for more than 5, we're looking for 6. We're not going to get 6 in 10 knots of breeze, right? Even maybe in 15 knots of breeze in the FJ, you're not going to get 6 knots. That's why most of the time you'll see pretty much most of the fleet is running downwind.